Okay, linear algebra people. We're going to take this story about vectors another step in section 5. So in section 5, we talk about vector form for answers, and then we start thinking about, again, span and where these guys map to and things like that. But this example here actually highlights or is an example of one of the theorems in section 5. So what we're going to do in this rather quick example is solve this system. There's two of them up here, actually. And we're going to compare the answer to see what we get. First, what we'll tackle is what they call the homogeneous system versus non-homogeneous. How can you tell the difference? You can tell when the equations are set equal to zero, they call it a homogeneous system. Okay, so we're going to solve it. Let's go work on the left-hand side. Okay, you notice if you take a quick look at this is that it's the same equations except one is set equal to 0, 0, and the other is set equal to, it looks like 1, 4. Okay, so we're going to set this up and we're going to go, okay, so 1, 3, and there's missing a third x, and then -4, and then if you want the 0, 0 over here, and 2, 4, 8, and -2, and we're going to row reduce it. Okay, so the row reduction would be, I think I'd go -2, row 1, add to row 2. Okay, so it's equivalent to 1, 3, 0, -4, oops, 4, and 0 and 0. Because you know what? A multiple of 0 doesn't change anything. I don't know if you've noticed. But here we're going to get a 0. We're going to go -2 down. So -6, 4 is -2. And 0 doesn't change anything. And -2 here is 8, -2 is 6. And you know, that's it. That's all we can say about it. It's in echelon form now. That's a 6. 6s, I have trouble with 6s. Okay. But anyway, did I do that right? Let's see. No, that would be -2. That's actually a 2. I can't even read my own numbers. So is it a -2? I think so. Right? So, yeah, okay. So let's take the bottom equation. The bottom row says -2x2. Start over. Okay, and then plus 8x3 plus 6x4 is 0. So all told, you can say that x2, when you divide over there, you're going to get a 4x3 and a 3x4. Okay, cool. Now let's back up. We're still kind of new to the game, right? Maybe I should have said something like, oh, I don't know. I've got a pivot here and a pivot here. Okay, and I've got free variable here and another free variable here. And that tells us two things, by the way. It tells us that later we'll say, oh, it maps onto R2 because I have pivots in each row. It spans all of R2. But since there's free variables, it's not one-to-one. So every vector you map over to R2, is this beyond us? I don't know, maybe. There's an infinite number of vectors in R4 that go to that particular vector. So it's all interesting stuff like that, how the functions play around. I just wanted to say that. And now I'm going to go back up and take the top row and go x1 plus 3 times x2. So it's going to be 3 times 4x3 plus 3x4. And then finally, what else do we have up there? -4x4, and that's equal to 0. Okay, so what is x1? x1 looks like it's 12x3, goes over to the other side as a -12x3, and then we have 9x4 minus 4 is 5x4, so it becomes -5x4, and that's your other guy. All right, now, I can do this really quick. It's not difficult, but the solution here is going to be a 4-tuple because there's x1, 2, 3, and 4. So you might say something like the answer, the vector that works is going to have this form. Well, the top one, the x1 is -12, x3 -5, x4. x2, we know, is 4x3 plus 3x4. x3 is just x3. He's free. You get to put whatever you want in there. And x4, same story. So all told, the vector form of the answer, okay, is equal to, I'm going to take out an x3. Anybody with that's a coefficient of x3, write it down. So minus 12, 4, 1, and guess what? 0. Because x4 is free. But then the next one is x4. And x4 is negative 5, 3, and now 0 and 1. And that is the vector form of the answer. What the heck does it mean? It's a way of writing the actual solution we might get in college algebra, but in terms of vectors. Because what we're learning is you can look at this as a matrix equation, and this 2 by 4 multiplies by a 4 by 1, and who goes to 0? These vectors. These vectors here of this form, and there's an infinite number of them because, you know, you could plug in 1 for x3 and 12 for x4. It's whatever you choose to do. So that's pretty interesting how we tend to look at things a little more abstractly. Now, if we quickly go to the other side, let's do this one. I'm going to set it up. And you know, the math is identical except for the last column. Okay, 2, 4, 8, negative 2. So row reducing, exactly the same move. 1, 3, 0, negative 4. And what did we get? 0, negative 2, 8, and 6. 0, negative 2, 8, and 6. But this time it's negative 2 times this guy. We've got to have a 1, and now we have a 2. Okay, so when we jump out and do the bottom row, it's minus 2 x2 plus 8x3 plus 6x4 is equal to not 0, but 2 this time. Look at the difference between homogeneous and non-homogeneous. You don't have zeros over there, you have numbers. So you write this and you go, well, x2 therefore is equal, as we found before, it's 4x3 plus 3x4, but what else? We have a minus 1 also. We have that too. So then we go after, that's done. We go after x1, and of course it's 3 times x2. And what is x2 this time though? What is x2? x2 is 4x3 plus 3x4, but what? Minus 1. And then minus 4x4. And what's it equal to? It's not 0 anymore. It's 1, isn't it? Okay, so we can, in our heads, maybe solve this. Once again, we get 12 x3, and so it becomes minus 12 x3, and similarly we get a minus 5 x4. Notice the similarity there, except for one thing. Here we have minus 3 comes over as a plus 3, and so you have a plus 4. So what does the answer look like if it's non-homogeneous? It goes x1 is minus 12, x3 minus 5, x4, but what else? Plus 4. What about x2? Well, that's the one that goes 4x3 plus 3x4, but something else, minus 1, and then x3, and then x4. And folks, let's write it in parametric vector form and make a comparison. I mean, these guys are going to be the same. We're going to say over here we have x equals that, and down here we have x equals, and it's going to be an x3 vector, and it's going to be negative 12 and 4 and 1 and 0. That's identical to over on the left. And then there's an x4 vector, and that's identical because it's going to go minus 5, 3, 0, and 1. But finally, there's this so-called constant vector, if you will. And the constant vector is, take it down, 4, negative 1, and there's nothing, and there's nothing. And there you go. I wanted to do this side by side so you can see this. Because when you take a look at theorem, let me see if I can find it in the book. Where am I? 1.5. I was just there. Theorem 6 on page 49. So theorem 6, page 49. It says, and I'm not going to quote, but it says this: the solution to any the solution to any non-homogeneous system has a solution to the homogeneous, that's this part, is identical to this part, plus a solution of the non-homogeneous. It's always in that form. He says it's something like W is equal to P plus VH. And what is W? It's a solution to the non-homogeneous. What is P? What is VH? It says, let's see, let P be a solution to this thing. So P is a solution to the non-homogeneous, and then VH is a solution to the homogeneous. That's why they give you the H there. And this guy, he's talking about this equation, AX equals B, in order to get to B. So what is B? B is this guy right here. And what is A and X? Well, we found the solution. X is this, the solution, and A is the coefficient system, right? A is this thing right here. Can you see that? Okay. All right. Anyway, there's a lot to that, but I wanted to see that side by side. You notice that the homogeneous solution is within, it's part of the non-homogeneous, always. Interesting. Okay. That's it for this one. We'll see you at the next section.